Welcome back, and let us resume our discussion on the simulation for the stability analysis for the common mode and differential loops. So, we have just looked into the common mode loop. Now, let us look at the differential mode operation and also the simulation steps required to analyze the high impedance resistor that we constructed using the transistors. So, let us look at the differential loop operation. For the differential loop, if I look at the overall scheme, so for the differential loop, if we assume that you have a same common mode loop for both of them and you have stabilized the common mode, so that this point is at the DC potential required to maintain an output common mode voltage equal to the required value. And therefore, for the differential loop, once again we have claimed that the same capacitor over here is going to compensate the differential loop as well. And to do that, we can check the overall differential operation and see how to calculate the loop gain for the differential operation. And remember, in order to look at the closed loop simulation, let us go to the block level and see the overall feedback scheme that we are implementing. So, assume that you have the feedback elements over here Z1, Z2, and your overall impedance or the ratio of the Z2 and Z1 gives you the gain, and you are having the DC potential over here set to AC ground. So, this is the scheme, and you are having the input signal applied over here. This is a single ended version. Of course, for the fully differential version, you can draw the other path also. You have the plus minus output coming in, and you have the Z2 Z1 feedback from the other side also. And using our discussions, we also arrived at the loop gain for this case. So, we said that the loop gain for the negative configuration, it was given by A naught, that is the gain of the amplifier times Z1 upon Z2, or in our case when you are using capacitor, it was A naught times C2 upon C1. If I call this C2 and C1, and we know that C2 upon C1 we are choosing it to be small because we want a large gain, maybe at least few tens. So, it can be from 30 to 50 or even 100. So, we are choosing the C2 upon C1 ratio fraction, a small fraction, and as a result the loop gain is definitely significantly smaller, much smaller than the open loop amplifier gain A naught that we are having. And in order to analyze the differential loop stability, one of the ways is to open the loop at this point. So, when we are talking about oscillations, we can set the input signal to 0 and look at the loop's behavior, what is the phase across the loop, and in that case we can break the loop at a desired point. In this case, let us assume that the loop is broken at this point. This is a relatively more convenient way of checking the stability, and almost a similar schema can be applied to the non-inverting configuration as well. So, here you are having the input signal, I am setting that signal to 0, that means this is now applied to the DC potential, and we are opening the loop over here, and that means that we will be applying the signal at this particular point, and we can test what is the feedback voltage coming at this point. So, overall after tracing the loop, what is the signal coming over here. So, we can open the loop and see that first of all you have to confirm that yes, the loop gain is same as what we expected using the shunt topology that we arrived at. So, we had discussed the overall feedback topology that we are having, and we arrived at the loop gain. So, if you are opening the loop at this particular point at the negative input terminal of the op amp, and then looking at the final voltage signal coming over here, we need to be sure that yes, your feedback signal over here, the overall transfer function between the Vt and the signal over here is also similar to what we achieved earlier. So, here we can see that the other terminal is at AC ground, therefore, the output signal over here is going to be A times Vt, and here you are having the Vf. If you look at the signal coming over here after this divider, that is going to be Vf, which is Z1 upon Z1 plus Z2 times A naught times Vt. And also we know that in order to get large gain, we are having the Z2 which is much larger than Z1. So, I can ignore the Z1 in the denominator, and then I have Z1 upon Z2 times A naught times Vt. And remember, we did a similar we took the similar approximation when we did the shunt feedback configuration and analyze that particular feedback configuration. We opened the loop by grounding the Z2 from the input point to the ground, and then we converted the input signal into equivalent current source, and then Z1 was also coming in parallel with Z2, and then since you had the in the parallel combination Z1 dominating, we took Z1 as the input point. So, there also we ignored this parallel combination of Z1 Z2. So, here also we are ignoring the Z1 in terms of Z2 in presence of Z2, because this is a much larger number, and therefore, we can see that the loop gain is same as what we expect, but we arrived at using the exact analysis as well. So, now in order to do the stability analysis for this particular amplifier, we need to apply a test signal at the negative terminal as we are seeing over here. So, our test signal will be applied here, and we need to look at the signal coming at this potential divider Vf to get the overall phase margin. And what we can see is definitely apart from A naught, you have this downscaling factor given by Z1 upon Z2, which is going to reduce my loop gain for the differential operation significantly as compared to the common mode case, and therefore, a reduced loop gain may automatically imply an improved stability for the differential operation. So, assume that for the common mode amplifier, common mode error amplifier, that was having diode connected load, and as a result the gain of that stage was relatively small, close to 1, and also the diode connected load do not provide significant impedance, and hence the poles provided by the diode connected load error amplifier would have been at high frequency. So, I do not really count the poles provided by the error amplifier, they are relatively at higher frequency, and also the gain of the error amplifier was significantly small. As a result, for the common mode feedback case also, the magnitude of the loop gain was similar, not exactly same, but similar. Now, why not exactly same? That you can recall that for calculating the common mode loop gain, you have to see the gain from this point to the output over here, the common mode output over here, and there rather than RO by 2 you get RO, because the impedance looking down into the drain of the MOSFET was pretty large. So, otherwise the order is similar. So, you have the gain from this point to this point given by GM RO, and finally, from this point to this point another GM RO by 2, and the common mode error amplifier, it is having close to unity gain, provided the error amplifier is having diode connected load. When I refer to diode connected load, that means both the sides having diode connection. So, in that case, the overall loop gain for the common mode is close to A naught, or of the order of A naught, very close to that, whereas for the differential loop, we are seeing that you have another factor Z1 upon Z2 coming, which is anyway suppressing the loop response or the loop gain. And if I look at the board plot, for example, for the magnitude and the phase response. So, what we are seeing is that the poles of these two cases, poles in these two cases are almost remaining similar, right. So, if I look at these two cases, for the common mode feedback loop, what we are saying is the critical poles are at this point and this point, and therefore, only thing is the impedance over here, if you are looking at the common mode analysis, rather than RO by 2 becoming RO, that is what we have discussed earlier, and we will go into that a little bit more detail. We will look into the derivation of the impedances at the cascode node when we look at the cascode or folded cascode amplifiers. So, if you are not clear about that, you can wait for a while. And the final output stage is also having almost the same small signal resistance and the capacitance. Therefore, the overall poles at these 2 points will remain almost close. So, so if I look at the phase response should be more or less similar. So, overall phase response, if I look at the first point, it will be showing 90 degree, and the second point approaching 180 degree, something like that. And the magnitude response for the original case, for the common mode case, if I say for the after the first pole minus 20 dB per decade and after the second pole minus 40 dB per decade, that is what we expect. If these are the P1 and P2, which are almost similar for the two cases. And now, if I look at the case of the differential response, for the differential loop, what we are seeing is there is definitely a shift in the gain. So, poles are remaining more or less similar. The gain, however, is shifted down, right, because you are having this C1 upon C2 or Z1 upon Z2 factor. So, the entire plot gets shifted down. So, I have this entire plot getting shifted down. Poles remain similar, only thing is the magnitude of the gain has been suppressed for the differential case, because you are having this additional feedback factor coming into picture in the open loop analysis. And therefore, if I try to compensate the common mode loop using a CC and try to make sure that you are achieving a 0 dB while your frequency reaches P2, I would say the differential mode is overcompensated, right. So, for that the phase margin will be even much better, because if you are assuming you are suppose I have drawn it such a way that the P2 lies. So, suppose my 0 dB point is coming over here, this is my 0 dB point for the common mode loop. The phase margin for the common mode loop will be given by the phase at this point, whereas for the differential loop the 0 dB point will be coming much earlier. As a result, the phase margin will be given by this point. As a result, the differential loop will automatically have a better phase margin as compared to the common mode loop, right. And that would imply that if I look at the stability of the common mode loop alone and try to compensate it using this CC, I will require a relatively large CC to shift my frequency response toward the lower side, or shift one of the poles towards the lower side. Whereas for the differential response, it will end up having even better phase margin, and because the gain is lower, we do not need so much compensation for the differential loop. Therefore, it may be better if we can decouple these two compensation and try to have more aggressive compensation for the common mode loop as compared to the differential loop. So, this is just one point before we go into the other amplifier topologies through which we can compensate the common mode loop separately and differential loop separately. We will look into that, but this is just to notify you of that point. So, what we are seeing is that for the differential loop analysis, this is the way we can break the loop, apply the test signal and observe the final loop response at this point. And for that, this is the overall loop gain A naught times Z1 upon Z2. And therefore, now if I want to look at the DC bias points to be taken care of while breaking this loop, let us draw the transistor level schematic and make sure that the DC bias points are maintained while we are opening the differential loop. We can, let me see whether we can it be done over here. So, when we open the loop over here for the differential case, both the sides we are ultimately going to put the Z1 upon Z2 from these two outputs to the ground. That is what we are doing. So, from both the outputs you will be putting the C1 C2 ratio that you have to the ground. So, for the fully differential operation, you are having the C1 C2 both connected from the output to the ground. So, and you are going to look at the feedback or the loop gain will be observed by checking these two signals while you are applying an input signal at the two inputs, differential input applied at these 2 points, and finally looking at the output signal over here. So, if I define this as my say positive input and negative input, I know that this is now going to be my positive output and this is going to be my negative output. As a result, if I want to see the overall loop response, if I apply a test signal over here, if I apply an overall test signal Vt between these two terminals plus minus, I will look at the final output response over here. This is your plus minus, so that I can get the overall loop response. And once again, while opening the loop, we have to make sure that the DC bias point over here is same as what we had during the closed loop condition. DC bias point over here is once again being provided by the common mode feedback, and if you assume that the common mode feedback is stable separately, this is not going to change much. So, all we need to do is use a proper DC bias point at both the terminals. So, assume that this is equal to the output DC common mode that we have set. So, you are going to have the VCM ref applied over here, same DC point. Remember, in our circuit also we have used the resistive feedback to set the input common mode same as output common mode. So, in this case output common mode point was over here if you are using the same common mode feedback loop, and therefore, I am setting the input DC level equal to the VCM ref, and on the top of that you will be applying a differential signal Vt. Likewise, here I can apply the same potential VCM ref and apply a differential signal say minus Vt. So, you put this Vt and reverse of that minus Vt can be applied over here. So, in that case it becomes a differential signal applied between the two inputs, and then finally, we are going to look at the output potentials over here. So, if the signal applied over here is anyway fully differential, the test signal that you are applying at the input is fully differential, the output signal over here is not going to have any significant common mode, therefore, common mode signal is anyway 0, and therefore, if you are having the common mode loop, you know that the output signal over here, the output DC potential over here is also going to the common mode error amplifier, and its feedback will be coming at this point. And since there is no signal, no common mode signal ideally at this point, that loop is not going to have any signal coming over here. This is just a DC bias point, and also here we have seen that for the combined common mode loop, if you are having a single common mode loop, we have also reduced the impedance of the common mode error amplifier by using a diode connected load, and as a result that is not going to contribute to a significant pole, and assuming that that stage whatever poles are coming, that is much higher than the poles coming at the two outputs of our main differential amplifier. So, if that assumption is true, I can just let the common mode feedback determine the DC bias point over here, and then apply the test signal plus minus Vt at this point, and look at the output potential signals coming at this particular point to observe my overall phase response for the open loop case. This is a capacitive divider, and here I do not so much worry about the DC potential. So, here I do not need to maintain DC potential. So, I just need to look at the AC signal over here. The DC potential should be maintained at this point and also over this point. So, in this case, since the common mode feedback is active, it will anyway make sure that output DC potential is close to the required value. So, I do not really need to worry about the biasing of the output DC potential, because that is already ensured by the help of the common mode feedback error amplifier, which is already making this output equal to the VCM ref. Only thing is that if you are getting rid of the resistive feedback, for simplicity, this RF that was connected between the input to the output side, if you are getting rid of that, then you will have to apply this DC potential over here. Remember, if you also, even if you keep the RF connected, if you keep the RF connected like what we have now, if you draw the RF, it will become complicated because you have the plus to minus coming. So, this has to connect here and this has to connect over here for the RF. Now, if I connect that RF and then assume that this DC potential will be determined by that RF, what will be the problem? If you apply an AC signal with 0 DC, the DC potential at the gate will be 0, right. So, if you assume that you have put the RF, the feedback resistor between the output and the input and the positive output and the negative input, like we did for biasing, and then you apply a test signal if the test signal is only AC with DC potential 0, that will set the DC potential over here also 0, and then your amplifier will not work correctly. So, in that case also you anyway have to put this DC potential over here equal to the VCM ref that you want. If you in that case the RF is not playing any role anyway, so you can eliminate it altogether. Even its presence will not matter much. So, you can confirm that okay, even if you have RF between these 2 points, that high impedance resistor that you implemented using transistors, even if you have that connected between these 2 points, it is not going to hurt much in the overall simulation, because there is very high impedance. Effectively it is not contributing much to the overall frequency response, apart from the, of course, you have the high frequency behavior that comes into picture when you look at the closed loop response, and you have that high pass filtering mechanism provided by this RF. But for stability analysis, it will not play a very significant role. So, to be accurate, you can always keep the RF over here, but even in that case you need to make sure that you are using a single source over here with a DC level equal to VCM ref, and then on the top of that you are applying the AC signal VT for testing, and then you are obtaining the output signal over here, and then phase response will be given by the gain from this point to the final output at the division of this capacitor. So, this is how you will be looking at the phase response for the differential operation.
Sir, we need this capacitor C1 at ground or some DC potential?
It will not matter much. It will overall response will not matter much, because this is anyway in the actual operation it is connected to the electrode, and you do not have much control over the DC potential over here. So, that is anyway decoupling the DC bias of the amplifier to the DC from the DC, any DC level that you may have the electrode. So, putting it is not very necessary to put an appropriate DC bias over here, because this is the input point, right. In your actual circuit, this is the input point which is coming from the electrode, and we do not have control over the DC potential provided by the electrode. So, even if you put it to AC ground, does not matter much, because anyway this is not passing any DC. So, it is not influencing the DC bias of the amplifier in any way.
How will RF affect the low frequency region, like you told now, it will give as a high pass filter?
So, we have discussed, right. So, while determining the value required for RF, we looked at the high pass response because of RF and the C2 that you have, and that must be able to pass the desired signal, and that only gave us the value of RF, because this RF produces a high pass response. That is what we had looked at. If you look at the RF, the way we created it using the transistors, you have remember the connections are only at the dot. Wherever you have the dot, this is no connection. And here also, in order to characterize this and try to find out the impedance of this, we can, one easy way to do it is apply a DC potential over here, which is VCM ref, and then apply same some VDC over here, and in the DC sweep analysis, basically you can try to look at the overall variation of the current across these resistors. So, you can put a marker over here, and then look at the overall or basically marker at the source of this PMOS, and then overall I you can plot as a function of VDC. So, VDC needs to be swept across VCM ref. So, VCM ref plus minus say plus minus 100 millivolt or even few tenths of millivolts, because remember these two potentials are not going to change too much. If the difference is too much, this resistor will not operate as a very high impedance device, because there are several other leakage mechanisms also which start building up when you have larger potential difference across this. So, for example, if you have larger potential difference between this point and the other point, so the potential between gate and the substrate also go on increasing. As a result, the gate to substrate leakage will also start increasing, and then in that case this device does not behave like a very good resistor. So, it will behave like a good resistor within some range, plus minus few hundred millivolt or across the zero potential difference. So, if I am looking at this VDC is at VCM ref, then of course the potential difference across these two is 0, and then if you increase it, the potential difference is increasing, and then if you decrease to VCM ref minus 100 millivolt, this is VCM ref plus 100 millivolt. So, if I am going from VCM ref to VCM ref minus 100 millivolt, the potential difference across this is negative, and if I am going towards higher one, it is increasing in the positive direction, and you can put the marker and try to see what is the overall current being transmitted from this point to the output point, and from there you can obtain the delta V, that is the potential difference between the two inputs, the two DC points, divided by the current flow, and that is going to give you the overall impedance. So, the impedance characteristics may look like something like this. For smaller differences, it gives you a high impedance, but as the potential difference increases because of increasing leakage components, say the leakage component between gate and bulk and the gate and the junctions, it will lead to reducing impedance. So, that is what we expect. If you plot the I divided by delta V, that is the V DC minus V ref. So, here I have plotted across the absolute value. You can plot it across the delta V also. In that case, this will be the origin 0, and you will have plus minus 100 millivolt on both sides, and then you can look at the impedance that is changing over here. So, this is the delta V upon I that you are plotting over here in terms of impedance. So, this is the whole characteristic that we expect. Remember, if you do transient analysis with this kind of resistor, because the resistor value is very large, it will give you a very large RC time constant. So, if you are trying to set up some transient simulation where such a large value impedance is connected between the output point and the input point. So, you are having this huge resistor that you have constructed using this transistor, and then you are having the input applied to the capacitor C1, and you are having some inputs applied over here. So, if you do the transient simulation, it will take time for the DC value over here to settle to the required value. So, in the transient simulation, therefore, this value may start from some arbitrary value, some arbitrary voltage, and it may take some time for this resistor to charge this voltage nodes to the values equal to the common mode output. So, in the transient, if you just calculate the RC time constant, it will be few seconds, order of few seconds. Therefore, if you are trying to run transient simulation for few milliseconds in order to simulate your low frequency signal, it may not settle within that duration. And in simulation, if you try to run simulation for such a long time, seconds, to just allow this potential to settle, it is going to waste a lot of time. So, one of the standard technique to do that or make it fast is to have some initial conditions. So, in the simulation, if you are putting some initial conditions, so that these two potentials are initialized to the value equal to VCM ref. In that case, you will not be dependent upon this resistor values to start from that or initialize or set up this value equal to the VCM ref. You are initializing this potential. That means, rather than starting with a random DC potential, the simulator will start by putting these two potentials at the VCM ref, and in that case, since these two potentials are anyway quickly set to the VCM ref by the help of common mode feedback, which is going to operate much faster, it will ensure that in the long run also, as your simulation goes on, this potential is maintained at VCM ref. So, while doing the transient analysis, you should just be careful of this fact that if you run the time domain analysis without initializing these two node potentials, it will take huge amount of time just for these potentials to arrive at VCM ref DC potential. So, you have to basically initialize it to the desired value and then let the transient simulation run. So, you should be careful about running the transient simulation with this kind of large value feedback resistors.
So, how to initialize by MOSFET switch?
That is another way, but you have simulation options are also there. We will check that in the LT-SPICE or even in Cadence. You have simulation options where you can apply initial conditions to some nodes. Even in the SPICE simulation, generally when you write codes for the SPICE simulation, there also you can specify initial condition using init statement. You can put some initial voltages at required points. So, other option is that if you want to use a DC source, so that you are connecting some switches over here, and t equal to 0, you have provided some DC potential over here, which is equal to the VCM ref as you suggested, VCM ref, and here also VCM ref. You can put this on for a very short time, and since this resistance is very small, the transistor resistance is anyway very small as compared to others. So, this will ensure that this is getting charged quickly, and this duration is very small. So, it is getting on temporarily and setting this to the required VCM, and then after that you turn it off so that it does not significantly affect your overall performance. That is also possible to do.
It should be 1 second approximately.
Because if you remember, we have used this in our earlier simulation when we did not consider the chopper operation and all. If you are just looking at the low cutoff frequency of around 0.5 hertz to 1 hertz to allow our content of the signal to pass. In that case, the cutoff frequency was chosen as around 1 hertz or lower than that, close to that. So accordingly, the RC time constant will be close to that. But now once we have chopper operation and we are relying on chopper to mitigate the noise, then of course we have seen that the entire signal is shifting towards higher frequency, and then you need to pass that high frequency, and you don't really need to worry about the 1 upon f noise so much. But in case, for example, in the next stage, suppose you have the first stage where you have the chopper applied, and after that you have subsequent stages. So chopper is generally represented by this kind of switches. So you have the chopper applied only in the first stage. After that you have the anti-chopper, and signal is coming back to the lower frequency, and then the second stage is having again that kind of capacitive feedback for further gain, or you are having filters with the help made with the help of these capacitors feedbacks and all. So for the second stage amplifier, once again you will need to apply that kind of feedback to settle the input potential at the same point, and then under that condition, once again since you have anti-chop the signal and signal is at low frequency, and you are not applying any chopping over here, so once again you may need to take care of the feedback resistor also. In many cases it may happen that you do not apply chopper after the first stage, rather than that you apply the chopper directly after the second stage only. That may also happen. In that case, both the amplifiers are basically processing high frequency signals.
So, but this simulator solves by using some mathematical equation. So why will it take 1 second or something like that?
It's not mathematical simulation. So if you are using time domain simulation, it is basically solving matrices at every time step. So just like you do KCL KVL, at every time step it will be solving KCL KVL, finding out the next DC condition for each circuit points, each nodes, and then again finding out the small thing, the resistance values and the capacitance values at every point, and again solving the KCL KVL at the next time step. So it is basically in the transient simulation it is something like a matrix simulation. Every time you have some spice circuit resulting from the DC conditions, you have some capacitor resulting from the MOSFETs, you may have some dependent current source which some values dependent upon the MOSFET parameters. So there are so many, these are the MOSFET also ultimately, even if you look at the large signal model, ultimately it will be breaking down into equivalent resistors, capacitors, dependent sources. So it will break down the entire circuit into these elements like resistors, capacitors, dependent sources, voltage dependent current source, current dependent voltage source, like that. And every time step, basically depending upon the DC condition, different nodes, the value of these capacitors, resistors will change. And as a result, once again taking the previous step values of the voltages at different nodes, it will try to solve the KCL for the next time step, taking the current values, and again find out the resulting voltage. And likewise, ultimately it forms a matrix of all these nodes. So when you solve KCL for large number of nodes, ultimately it is a form of a matrix, and it solves that matrix for every time step while updating these capacitance values, resistance values, which are bias dependent or voltage current dependent. So every time step it will keep solving that matrix. Therefore here also it will do the same thing. So it is something like doing the exact behavior simulation. So it will simulate in a way the real current is going to flow, and it will take as many time steps to settle the value as it would require for a real circuit, means in terms of simulation step. So in the real circuit, of course, if it will take say 1 second to settle this voltage to the required value. Likewise, in the simulation, to simulate that 1 second, it has to simulate so many matrix equations depending upon your step size. So it will take many such matrix equations, and finally you will be arriving at that 1 second point.
Sir, in the simulation, current flow both PMOS are different.
So that may be because having the bulk contact also. So since you are talking about very small current and the potential differences are increasing, so the bulk to substrate to gate potentials are decreasing or changing, and as a result you may have some leakage paths also which are contributing to the current. So if the potential difference increases, all those leakage paths also become stronger. As a result, you will not get exactly same current, you have other paths also from the leakage.
So in the calculation of resistance, which current you have to consider?
The best thing to do is look at the so this is valid mainly in the small region. So as long as the voltage differential across these two is small, few tens of millivolt to 100 millivolt, it is valid. After that, anyway, this will start dropping because of other leakage currents coming into picture. So strictly speaking, this is the right region. Beyond that, because leakage starts dominating in other paths, it will not give you a very high resistance. The better way to do is you put a small resistance over here, and then measure the current flowing here and measure the current flowing here, or even from the sources you can in the select the upper terminal of the sources in the simulation. That will also give you the current flowing through the sources and both the sources. So you can check how different they are. That will give you that will tell you that okay, in the central region maybe it will be very close, but as you diverge from this two, it will become different. So this scheme will be valid only for this central region where other leakage components are not very significant. Especially the gate to bulk leakage, and likewise we are having the bulk to junction leakage. They are not very significant. As the potential difference starts increasing, then both of them will be having more leakage component, other leakage component coming into picture. Here we are interested in source to drain current, other leakage component like junction to bulk leakage or gate to bulk leakage that will destroy the characteristic that we are looking for. So as the potential difference across the gate and the source increases, or gate and the bulk increases, it increases all those leakage components exponentially, because that is mainly based on tunneling effects. Especially if you go for scale technology, 180 nanometers, still it is okay. If you go for more scale technology, those leakage components will be even stronger, and implementing this will be more difficult. In fact, you will have to go for higher oxide thickness MOSFET so that those leakage components don't come into picture. Even if you look at the AC analysis, if you are putting an AC signal over here and trying to do AC analysis, there also you have the other parasitic capacitances coming into picture. So that will also not give you the right R value. So I can think about three analysis, either DC, AC, or transient. So if you do transient, definitely that is not a good way, because it is going to have very large RC time constant, and it is not going to let the current flow as fast as you want. The other option is if you are doing AC analysis, you put the AC frequency very low, maybe 0.1 hertz or something like that, and then the time step in the simulation has to be reduced accordingly. So increase accordingly. So if you increase the time step in the simulation and then use a very low frequency AC, maybe 0.1 hertz or something like that, then still AC analysis will be able to work. So only thing is the AC frequency you are applying over here for transient, that should be much lower within the RC time constant provided by this transistors. So then it will still work. For that, you need to select an AC signal with frequency very low and use a very large time step, so that for a given long duration, say few seconds, the signal is able to follow the applied or the current is able to apply the applied signal. Okay, so resume our discussion in the next session.